Hello everyone. Today I will present the paper Word E, Word Alignment by NeuroSymbolic Learning Improves Word Model-Based LLM Agents. This paper asks a simple question. How can we help an LLM agent understand the actual dynamics of a new environment more accurately? The key idea is not to rely only on the LLM's general common sense. Instead, the method extracts symbolic knowledge from real experience in the environment and uses it to correct the LLM's word model. So the goal is to align the LLM to the environment and make planning more reliable. In this talk, I will first introduce the motivation and related work, and then explain the method step by step, and finally show the evaluation results. Let's start with the main motivation. Many previous works try to use the common sense already stored in an LLM. This can work well in normal environments, but it becomes much harder in counter common sense settings. For example, imagine an environment where cows shoot arrows or diamonds can be mined with a wooden pickaxe. In this case, the LLM's prior knowledge conflicts with the actual rules of the environment. So the main problem is the gap between the LLM's prior and the real environment dynamics. The authors call the process of reducing this gap word alignment. In short, this paper tries to answer why does a strong LLM still fail in a new world, and how can we fix that with real experience? The first line of related work is model-free LLM agents such as React, Reflexion, and Skill Library. These methods usually follow a simple pipeline: observation, then LLM, and then action. So the LLM decides what to do directly without using an explicit word model. This is simple and fast, but it also has a limitation. Because the agent does not simulate the future well, its look ahead planning is weak. As a result, it can make unsafe or suboptimal decisions. Where it tries to address this by giving the LLM agent a usable word model so that it becomes a model-based LLM agent rather than a purely reactive one. The second line of related work is symbolic word model construction, such as other planner and word coder. These approaches use an LLM to build a symbolic model of the environment, and sometimes even convert it into executable code. According to the authors, the limitation is that a large part of the environment still has to be modeled symbolically. That can make the approach harder to scale and less efficient. Their argument is the following. An LLM already contains a lot of general knowledge about dynamics, so we do not need to rebuild the whole world symbolically. Instead, we only need to add a small amount of missing symbolic knowledge. So word E is not full symbolic model construction. It is more like an LLM word model plus symbolic correction. Now let's look at the overall framework of word E. The main idea is that two modules run alternately. The first is NeuroSymbolic learning. This module extracts symbolic knowledge from real trajectories, compares real and predicted trajectories, and turns the learned knowledge into executable code rules. The second is Model Predictive Control, or MPC. Here, the agent proposes an action, the word model predicts what will happen, and the rules check whether that prediction is valid. If not, the agent plans again. So, in one sentence, the learning module improves the word model, and the planning module acts using that improved model. Now, I will explain this process from stage 1 to stage 4. This is stage 1. The first step is to compare the real trajectory from the environment with the predicted trajectory from the word model. Each transition is checked based on whether it is predicted as a success or failure. An important point here is that symbolic knowledge is extracted only from real trajectories. The incorrectly predicted transitions are not used directly for symbolic learning. Instead, those incorrect transitions are kept for stage 4, where they are used to evaluate which code rules actually fix mixed predictions and should remain after pruning. From stage 2, the method extracts 3 types of symbolic knowledge. The first is action rules. These are rules like under this condition, this action fails. For example, a rule may say that the make action fails unless a table is nearby. So this step captures direct constraints that determine whether an action can succeed or not. The second type is the knowledge graph. It stores prerequisite relations between entities such as items, materials, and tools. For example, to make item A, you may need X units of B and Y units of C. So while action rules describe local action constraints, the knowledge graph represents a higher level structure, what depends on what and what resources are required. This helps the agent reason over longer chains of actions. The third type is the scene graph. Unlike the first two, this one focuses more on scene and location information than on action rules. It accumulates spatial information to handle partial observation. For example, it can keep track of which item was seen in which room or where a certain object was located before. This is useful because the task setting is a POMDP, where the agent can observe the full state at once. So the scene graph works like a memory of the global scene, including things that are no longer visible in the current prompt. In stage 3, the symbolic knowledge is no longer kept as plain text. Instead, the LLM converts it into executable code rules, usually in the form of Python functions. Each rule returns 3 things: feedback, a success flag, and a suggestion. This is important because the symbolic knowledge is no longer just a description inside a prompt. It becomes a callable checker that can test whether an action violates an environment constraint. So I think of this stage as turning symbolic knowledge into executable symbolic constraints. However, not all generated rules are useful. Some may be wrong, redundant, non-executable, or simply not helpful. So in stage 4, the method performs rule pruning. The process is simple. First, rules that do not match real trajectories are removed. Second, rules that produce runtime or logical errors are removed. Third, among the remaining ones, the method keeps the subset that fixes the largest number of incorrect transitions. The paper formulates this as a maximum coverage problem and solves it with a greedy algorithm. So the goal is not to keep many rules. It is to keep a small and effective set of rules that reduces LLM prediction errors the most. The authors also show that without pruning, rule conflicts can hurt the performance a lot. Now let's see how inference works. It has 4 steps, step A, B, C, D. In step A, the LLM agent looks at the current observation and proposes an action. In step B, the LLM word model predicts the result of that action. If this prediction conflicts with the code rules, the system feeds back the rule outputs such as feedback, suggestion, and success flag and asks the word model again. The paper calls this step online. The key point is that the code rules do not replace the LLM. They act as corrective constraints. Then in step C, if the flag is positive, the action is executed. If not, the agent replans using the feedback. So the full loop is propose, predict, verify, and replan if needed. Now let's move to the evaluation. The paper mainly experiments on Mars, which is a 2D Minecraft-like open-world environment. The main goal is to mine diamonds. What makes Mars interesting is that it includes counter-Commonsense settings. So the environment is intentionally designed to conflict with the LLM's user prior knowledge. The evaluation uses the reward defined in Mars. For example, unlocking an achievement gives positive reward, while health loss gives negative reward. The assumption is simple. A higher reward means the agent is getting closer to the final task. For the main result, the authors claim that WAR-E is one of the strongest training-free methods. Here, training-free means that the method does not update the model parameters through gradient-based optimization. So it adapts to the environment without standard model training. This is especially meaningful in Mars, where the LLM's prior often conflicts with the true environment rules. The paper reports that compared to baselines, where it improved success rate by 16% to 51% and improved score by at least 61%. It is true that training-based methods like Dreamer v3 achieves higher absolute reward. But Dreamer v3 uses about 1 million environment steps, while WAR-E uses only about 5,000 steps. So the focus here is not maximum absolute performance, it is few-shot adaptation efficiency. Finally, the authors explain why performance improves by using a metric called cover rate. Cover rate is the fraction of wrong transitions from the LLM word model that are corrected by the newly learned symbolic knowledge. The results show that as the number of iteration increases, coverage increases, and reward also increases. This suggests that the symbolic knowledge is actually making the word model more accurate. So the main takeaway is this: instead of relying only on prompt engineering, this paper extracts symbolic knowledge from real experience, turns it into executable constraints, and uses it inside planning to achieve practical word alignment. Thank you for listening.